Hi there, folks. Today we're looking at circumference and arc length. All right. And circumference, hopefully, is one of those things that you already understand. Remember, it's like the perimeter of a circle. It's the distance around the circle. And we have two formulas that we use for finding the circumference. There's the classic 2 pi r is the one that's used the most often. Thinking about things in terms of the radius is nice because our other formulas use the radius as well. But you could also do pi d, and really these are the same formula because remember the diameter is 2 of the radius. So here's 2 times the radius. Well, that equals the diameter. Okay, so saying 2 pi r versus pi d means the same thing, but that's how we find the circumference, which is the distance around this circle. It's like the perimeter of the circle, all right? Concentric circles are basically circles that are inside of one another, so coplanar circles with the same center. So if I have two circles that are maybe different sizes placed at the same center, what I get is one circle inside of another circle. Those are concentric circles, all right? So kind of looking like this. If I have one circle placed inside of another circle and they both have that same center, those are concentric circles. You can kind of think about like a tire. If you look at a tire, it has one circle on the that kind of marks the inside of the tire where it meets the rim, and you have one side of the circle that represents the outside of the tire that kind of meets the road. All right, and so that's what we're looking at when we talk about concentric circles. Okay. For example, applying concentric circles and circumference in kind of the same aspect here, it says a 2-foot wide track has an inner diameter of 8 feet. If a cart is placed on the track, how much further will the outer wheels travel in one rotation? And so it's one of these tracks, almost like a train track or something like that, where the wheels kind of lock onto that portion of the track. And so if we were kind of to draw a picture of this thing, so there's the outside of the track, and then we have the inside of the track, which is 2 feet away the whole way around from the outside of the track. And so as we kind of start to label this thing, it says the has an inner diameter of 8 feet. So if I were to kind of mark this from here to the outside of the circle, or see, or from here to the circle, that's 8 feet. But then it's a 2-foot wide track, meaning that the whole way around here, so like this piece right here in red, that's 2 feet. Likewise, on the other side, that's also 2 feet. So it's 2 feet no matter where I go. I just happen to draw it like I could draw that anywhere. Hey, it's 2 feet here. It's 2 feet over here. The reason that I have it drawn here, the reason I drew it there, is to kind of show this thing as an extended radius, because what I need is the radius of not only the inner circle, but the radius of the outer circle as well. Okay? And so when I compare these, when you think about this thing rolling around the track, the distance that it covers is going to be the circumference. So the inside wheels, the distance that they cover, is going to be the circumference of this inside circle. Okay? And the outside wheels, the distance that they cover is going to be the circumference of this outside circle. That's how far they're going to travel before they get back to where they started. So in one rotation, the inside wheels are going to travel not quite as far as the outside wheels because they're on the track that represents a smaller circle. And so we want to compare these. What we want to do is we want to find the circumference of each. And so the circumference of the smaller circle, or I guess we could call it the inner circle, okay, would be 2 pi r, so 2 times pi times the radius, which is 8. And so the circumference of the inner circle is going to be 16 pi, all right? The circumference then of the outer circle, when you look at the outer circle, that has a radius of 10 because of the extra 2 feet, so 2 pi times 10. So that has a circumference of 20 pi. And so the question asks, how much farther did the outer wheels travel? Well, this is a job for subtraction. So I do 20 pi minus the 16 pi. And notice I'm leaving everything in terms of pi until I get to the end of this thing, okay? So 20 pi minus 16 pi, just like combining a 20x minus a 16x, that's going to give me a 4 pi. And so now saying 4 pi feet that is an exact answer, and that would be true. But based on the context of the situation, let's plug this one into a calculator. So I'm going to hit 4, and let's use the pi button for this. It's okay to use 3.14, but it's a little more accurate to use the actual pi button, okay? And so we hit 4 pi here, and I get a 12.57. Okay? And when you think about that, this is like one of those reasons why you have to rotate your tires and that kind of thing. As you make turns and stuff like that on your car, one side of your car actually travels further than the other side of your car in terms of the rotation of the wheels, okay? And so because of that, you get different stressors and different wears in different places. And if you make more right turns than left turns, you might get uneven wear on your tires because the outer tires are traveling farther than the inner tires, okay, as you make those curves, all right? And so that's part of the reason we rotate tires, that kind of thing, all right? But in this example, if this cart is going around this circle over and over again, eventually you're going to have to replace those wheels that are on this cart. And the outside wheels are going to wear out faster than the inside wheels because they're traveling a longer distance, okay? Let's talk about arc length. Arc length is basically a partial measurement of the circumference of a circle. And so we've talked about the measurement of arcs in terms of degrees. Now we're going to talk about the measurement of arcs in terms of a linear distance, in terms of a length of some kind. Okay? And so again, it's just part of the circumference. When you think about this, an arc is part of the circle. The circumference is the whole way around the circle, so the arc length is going to be part of the way around the circle, all right? And so one of the ways I like to think about this is as a fraction of the circumference, and that's probably the easiest way to find these, is thinking about it in terms of a fraction. We'll also use proportions for these, but the easiest and fastest way to do it, I think, is using a fraction, okay? When you think about the arc, it's a fraction of the whole circle. It's a part of the whole circle, which means the length of that arc is a fraction of the entire circumference, okay? So arc length, the ratio of the arc length to the circumference is equal to the ratio of its corresponding central angle to 360 degrees, all right? And so we're just comparing the different versions of measurement for arcs, okay? When you think about the measurement for an arc, you can measure it in terms of degrees, but now we can also measure it in terms of length. And so what we do here is we kind of look at it this way. Let's say that an arc has a measurement of 20 degrees. Well, the 20 degrees would be like the measurement of that arc compared to the whole circle would be 360 degrees. And then to find the arc length, well, the whole circle has a length of 2 pi r. I can then find the length of the arc by cross-multiplying, okay? So it's this idea of proportionality based on the fact that, hey, if this thing represents part of the degrees of this thing, that ratio of the degrees that it represents over 360 is the same ratio that we're going to get if we compare the actual arc length to the whole way around the circle of 2 pi r, okay? And so it's just this idea of partial arc over the whole arc in terms of the degrees equals partial arc over the whole arc being the circumference in terms of a length, okay? So again, it's just part over the whole equals part over the whole, where we're just representing, the arc over the entire circle still equals the arc over the entire circle, whether we're talking about degrees or lengths. Okay? And so this is the proportion that we can set up in order to solve for arc length. Okay? So this means that the arc length can be found using proportions, or we can multiply the circumference by the angle ratio, and we'll talk about that in a little bit, if we think about this as a fraction of the entire circumference. Okay? So here's how the two of these work. Taking a look at this guy, it says find the length of the arc x. Okay, so I want to find this arc length. And again, this arc length represents part of the entire circumference. It's not the whole circumference, it's just a small piece of the circumference. Okay, and so if we kind of think about the arc length, the arc measurement in terms of degrees, the degree measurement for this arc would be 50 degrees. Okay, and now if we compare that to the entire circle, the whole way around the entire circle, well, that's 360 degrees. And so if we kind of think of that as a ratio, the 50 degrees compared to the 360 degrees. So the angle of the arc over the angle of the whole circle, it's going to be the same ratio that we get when we compare the length of the arc over the length of the whole circle, okay? And so for this one, it's going to be x over, well, this is going to be 2 pi r, which the radius this time is 4, so that's going to be 8 pi. That's the circumference. And again, we're just thinking about this in two different measurement types. When you think about it in terms of angles, the arc is 50 out of the 360 degrees, and that's what this first ratio says, okay? But the length of this thing, sorry, I went to try to erase this, but the length of this thing, well, the partial arc is called x, but the whole way around this circle would be the circumference. It would be 2 pi r, which is 8 pi, okay? And so really I'm just doing the same ratio. I'm comparing the arc to the whole thing, but I'm comparing it in two different measurement styles, okay? When I look at degrees, arc to the whole thing is 50 out of 360. When I compare the lengths, the arc to the whole thing, it's x compared to the 8 pi. The point here is that no matter which ratio I do, they're actually equal to each other. And that's what I have set up here. So again, it's just part over the whole equals part over the whole, okay? The partial measurement in terms of degrees over the whole measurement in terms of degrees, the partial measurement in terms of the length over the whole measurement in terms of the length. And now I can cross multiply and solve this thing. So here I cross multiply, that's 360x equals, that's going to be 400 pi. And once again, I leave it in terms of pi until I'm to the end of this thing, okay? And I'm going to divide each side by the 360. So I end up with x equals, I could reduce this fraction and leave it in terms of pi if I wanted to. In fact, maybe I'll do that because, you know, really just there's different scenarios. This one we don't really want in terms of pi. It's not a measurement that necessarily makes sense, but this is going to be like 10 pi over 9 if I reduce it. So now let's plug that into our calculator. So I get 3.49. And there were no units given here. If that measurement in inches or in for the radius was in inches, well, then this would be in inches as well, okay? But it's just approximate measurement, all right? So that's option one, setting up a proportion. Again, as long as you remember, hey, it's just the same ratio whether I do degrees or whether I do length, and it's just part over the whole equals part of the whole, okay? The arc measurement over the whole measurement equals arc measurement over the whole measurement, all right? And then I cross multiply and solve. The other option is to just look at it this way. Just look at it and say, you know what? That arc is a fraction of the entire circle. And the fraction of the entire circle that it becomes is 50 out of 360. If you kind of just think of that as a fraction, as saying, hey, that's 50 of the degrees out of the 360 degrees. So this represents a fraction of the circle of 50 out of 360, okay? Which of course reduces to 5 over 36. So if I said, hey, what portion of the circle does this represent? You would say, oh, it represents 5 out of 36, okay? 5/36 of the circle, okay? So basically that is a fraction of the whole circle. And so if you think about that, it's going to represent a fraction of the entire circumference. Well, watch this. If I take the circumference, which is 8 pi once again, well, instead of having the entire circumference, like if I had a semicircle, I would only do half of the circumference. If I only had a quarter of the circle, I would do a quarter of the circumference. If I only have 5 out of 36 of the circumference, well, then I do 5 out of 36 times the circumference, okay? And as you multiply this out and simplify, well, you get 10 pi over 9. You get the exact same thing because it represents the same thing. So you can either do this by proportions and cross-multiplying, or you can say, hey, you know what? That's a fraction of the whole circle. So once I know what fraction of the whole circle it is, I can find the measurements by just multiplying everything by that fraction. I multiply the circumference by that fraction, and I still get to 3.49, okay? And there are advantages and disadvantages to these. I think students find setting up the proportion much easier because it's just partial over the whole, and it's always, degree over 360, okay? It's always length of the arc over entire circumference. So memorization-wise, it's easier because you always have set values that you plug in here, okay? But again, the doing it as a fraction just makes more sense in terms of being able to do this quickly. For example, if I look at this guy, again, I'm going to do the fraction version first this time. When I look at this thing, first of all, we got to be careful because we're looking for this value, all right, which means I want to look at this angle instead. So instead of the 175, I actually have to subtract that from 360 and find the other half of this thing. This is 185 degrees for the portion that's represented by x. So just make sure you're finding the right portion of this thing, okay? And so if I said, what fraction does this represent? This arc is a fraction of the whole circle. Well, the fraction that it represents is 185 over the 360, okay? It's part of the entire circle. And if I just write that as a fraction, I can reduce that thing. They're each divisible by 5 for sure here. And so if I divide each of them by 5, that gives me a 37 over 72. And it doesn't look like that's going to reduce any further because 37 is a prime number. So that's the fraction that it represents. And so if I wanted to find the length of that piece, it's just a fraction of the whole thing. So I say, hey, you know what? Let's start with 2 pi r. So the circumference is 18 pi. But I only want a fraction of that circumference, and the fraction that I want is 37 over the 72. All right? And so once again, this can be a job for my calculator here. Again, if I wanted the exact value, I guess I could work that out first. Here, the 18 and the 72, those are going to reduce. They're each divisible by 18, actually. And so that's going to give me a 1 pi, so that's going to be 37 pi. Over the 72 divided by 18 is going to give me a 4. And so that's the exact value in terms of pi, but we don't really need the exact value in terms of pi. What we need is the rounded off answer. So I'm going to do 37 pi divided by 4. And I get 29.06. And there were no units given here, so that's it. That's my answer, okay? So I look at it in terms of a fraction. All right, the arc length is a fraction of the overall circumference. The other option, once again, is to do this as a proportion. If you're going to do it as a proportion, again, you just compare the angles. You say, hey, the part that I have, so it's part over the whole, which is 185 over the 360, equals the part over the whole for the lengths, and that's going to be x over the entire circumference, which is 18 pi. Right? So these are the two options. You either say, hey, it's a fraction of the whole thing and you multiply, or you'd say, hey, it's proportional in terms of the whole thing. So the partial measurement over the whole measurement equals the partial measurement of the whole over the whole measurement. Now I cross multiply. Over here, again, use your calculator a little bit. And now you divide each side by that 360. And this one might be a little bit harder to reduce in your head. You need to use the calculator a little bit for this. You will get the same thing. I'm just going to plug it right into the calculator for the decimal approximation. It was the 3,330 times pi, and then divided by the 360. And there it is, 29.06. Okay, so you either set up a proportion between the angles and the lengths, or you say, hey, it's a fraction of the overall circumference, so I just multiply by that fraction. Okay. If we look at this one, it says find the arc length if the radius of the circle is 3 inches and the corresponding central angle measures 135 degrees. And so once again, maybe draw a picture of this thing if you want to visualize it and say, okay, I've got the radius here of 3 inches, okay? And it says the central angle that I'm talking about is 135 degrees. And so from here, I just need to find the entire circumference. So once again, that's 2 pi r, which is going to be a 6 pi for this one. So that's the entire circumference, but I only want a fraction of that circumference. Well, think about the fraction this represents. This represents 135 degrees out of a total of 306 degrees. So the fraction that represents, and really, if I want a decimal approximation for this thing, we've been reducing the fraction, that kind of stuff. For this one, let's say we just want a decimal approximation. I don't even need to reduce that fraction. I don't even need to put the work in to reduce that because the calculator doesn't care if this thing's reduced. And so for this particular example, I'm just going to go ahead and plug it right in. So it's 135 divided by 360. And then times the 6 pi. And so it gives me 7.07. And this time I do have units, that's in inches because we're talking about a linear type of measurement. Okay, it's being measured around the curve. And once again, if you wanted to do this in terms of a proportion, you would still use that same fraction. That's your first ratio. It's the 135 to 360 equals the partial measurement over the whole measurement. Okay, and then you could cross multiply and solve, and it should give you the same thing. Okay. If I look at this one, find the value of theta. This is a variable that we use a lot of times when we're talking about angles. You'll see this come up in pre-calc a lot, but instead of using something like x, we use theta. It's just one of those things that we like to use for angles, okay? And so I want to find theta. Again, it's just a variable. And so this time I'm kind of working backwards here. And when you think about it, I have this guy. I have the radius this time. So I have the entire circumference of this thing. So the entire circumference of this guy is 6 pi once again. But now instead of looking at this from the perspective of, I have a fraction in terms of the angle, what's the fraction for the arc length? I can do the same thing, but in reverse. When you look at this guy is a fraction of the overall circumference. And so the fraction of the circumference that this represents is 2.356 over the 6 pi. So kind of working backwards here, I want a fraction of the entire degree measurement this time. And the fraction that I want, see, the entire degree measurement is 360. And the fraction of that I want is the 2.356 over 6 pi. Okay, so I'm still doing the same thing, but now I'm doing it in reverse. Now the lengths are giving me the fraction, and I want to find a fraction of the entire degree measurement. Okay, and so again, the calculator does the work for us on this one. 2.356 divided by 6 pi, and now times the 360. And so I get 44.996. If I round that, it ends up being 45 degrees. And so this is a 45-degree angle, all right? And again, we could set this up as a proportion. If I did it as a proportion, it's the partial angle, which is theta, over the entire thing, which is 360. Again, I compare the angles as a fraction, equals compare the lengths as a fraction. This time it's 2.356 over the entire circumference, which is 6 pi. And now once again, I cross multiply and solve. And if I do that, I end up with 45 degrees. Okay?